The other topic in this section, which is closely related to linear approximation, is differentials. So if I start with a differentiable function, y equals f of x on an interval containing a, the x coordinate, and let the x coordinate change from a to a plus delta x, we find the differential. So the differential, if x is a differentiable function, a small change in x is denoted by the differential dx. The differential dx is a small change in x. The corresponding change in f is approximated by the differential dy. The differential dy is equal to the derivative times dx. So if I look down for the use of this, delta y, which is the difference in the two y coordinates, is approximately dy, which is the derivative times the differential dx. So delta y is the actual difference. Real difference, and dy is its approximation. Oftentimes in a real world setting, it's hard to know what the actual change in the output is, but we can approximate the change in the output easily if I have a function in a differential. So the first thing just to note is we've done derivatives before in plenty of times. So I've done a derivative like, first of all, I can just say that I know that there were two forms for the derivative, dy dx and f prime of x, so Newton's and Leibniz's forms. So if we consider that the derivative operator, this differential right here, can be separated, if you pretend to multiply the dx to the other side, then you have a statement dy equals f prime of x dx. That's the backbone of writing differentials. So to write a differential, I just need to find the derivative and then multiply the dx to the other side. So I'm going to practice that a few times here, then we'll use it in an example on the next page. Okay. So if I have a function, y equals f of x is tan squared of x. First of all, don't forget that tan squared of x is shorthand for tangent of x quantity squared. So the first thing I can do is compute the derivative. So dy dx is 2 times tangent of x times tangent's derivative, which is secant squared of x. Okay, so that's a derivative, not a differential. But if I move the dx to the other side, I'll have the differential. So the differential is dy equals 2 tan of x times secant squared of x. And so this is the differential. Now, there are, of course, two differentials here. I of course didn't even write my dx. I said I was going to. I forgot to write it. There are now two differentials here. dx and dy are both differentials. But this is now in differential form as opposed to in derivative form. Okay, let's look at the next one. We'll start with the derivative. dy dx, quotient rule here. So bottom 4 minus x times the derivative of the top, which is 1, minus top, x plus 4 times the derivative of the bottom, which is negative 1, over bottom squared. This should simplify. I have 4 minus x. Those two negatives make a positive, so plus x plus 4 over 4 minus x squared. So that comes out as 8 over 4 minus x squared. That is the derivative. So the differential dy would be equal to 8 over 4 minus x squared dx. Now, sometimes that differential is written in the top, so you could also see that written, since it's just a multiplier right now, as 8 dx over 4 minus x squared. So that's another way of writing that differential. So again, we have the derivative, dy dx, and if you separate the two parts of that into a differential, you have in differential form. Now, that's just a little practice on doing differentials. Now, on the next page, we'll practice an example of where they might come in handy in a word problem, some kind of real type situation. So I want to use differentials to approximate change in volume of a right circular cone of fixed height 4 when the radius increases from 3 meters to 3.05 meters. Okay, so the first thing I need is volume of a cone. So the volume of a cone is pi r squared h, and we have a fixed height right here, fixed height of 4. So I'm going to go ahead and plug that in because it's not a variable, it's a fixed value. So my volume is going to be 4 pi r squared if I multiply that 4 into the front there. Okay. Now the first thing I'll do is find the derivative with respect to r. So if we take dv dr, it's going to give us 8 pi r for the derivative. The derivative of r with respect to r is 1, dr is 1. This is the derivative. Now we're going to get it in differential form. So in differential form, we're going to say that dv is 8 pi r times dr. Now we're going to be able to estimate the change in volume because dv isn't the change in volume. The change in volume is delta v, but delta v is approximately equal to dv, which is equal to, I know that r increases from 3 to 3.05, so that means that I'm going to use an r value of 3 and a dr value of 3.05 minus 3, or positive 0.05. So my change in volume is approximately 8 pi times 3 times positive 0.05. Okay, so first of all, if we just compute the non-pi values, we have 8 times 3, which is 24, times 0.05, so that's 1.2 pi. And then if I put the pi in there, we can get an approximate value for that. So 3.7699. And our units were meters, so that's going to be in cubic meters. All right, so in conclusion, we can say that change in volume or delta V is about 1.2 pi cubic meters, or 3.77 cubic meters when the radius increases from 3 meters to 3.05 meters. And this is something that, again, might be hard to measure. You can measure it with liquid and so on if you needed to measure it. But if you don't have the object, again, you can approximate what would happen in that situation.